Good evening, friends. We are going to deal with the eighth presentation of this series on chemical energy to electrical energy. Now, this will be a short presentation because of certain limitations here, but we will be coming back with a greater time scales in the coming days. Now, what we are trying to do here is to understand the some basic principles of catalysis, basic principles of electrochemistry. Now, we have so far seen the fundamentals of the electrochemistry. Now, we have to understand a little bit on the fundamental types of overpotential. This overpotential is a very a concept which has to be understood in a very uh, technical manner. When electrons are metallic ions pass, that is when the electron transfer is taking place from the electrode, or a metal is getting oxidized, for example zinc going to zinc 2 plus, uh, ions pass through the interface of a simple electrode. A thermodynamically defined reversible electrode potential is set up. This equilibrium involved is a dynamic one. Okay, just like any other equilibrium process, this is also a dynamic one. Okay, so what it only means is that the rates at which charge carriers pass through the interface in either direction are equal. That is, ion is getting metal is getting ionized. Some ions are capturing the electrons from the electrode. In other words, the exchange current density that we see I0 is same in both directions. In the anodic and cathodic partial current densities, or if we have to represent them as I plus and I minus, then at equilibrium, I plus will be equal to I minus will be equal to I0. This is called the exchange current density. Okay, please note this parameter very carefully. We have to use this parameter extensively later on. Overpotential may be observed when an additional external current is superimposed on the system by means of a suitable counter electrode, as occurs, for example, during electrolysis or during withdrawal of current from a galvanic cell. The electrode will then assume a potential EI, which is different from the E reversible. Okay, which will differ from the equilibrium value to an extent governed by the current density. The differences between EI and the equilibrium potential E reversible is known as the electrical overpotential, which is generally denoted by eta, so that eta will be equal to EI, the assumed potential under the conditions, minus E reversible. When no thermodynamic equilibrium potential is established for zero external current, then the difference of the potential at I is equal to 0 and I is not equal to 0 is termed as polarization. Okay, eta is also called the polarization. It is called the EI minus E0. In some cases, E0 is equal to E reversible, that is, polarization or potential are equal to each other. That is why we have defined already over potential and polarization are similar concepts. E0 is not equal to E reversible is realized when the electrode potential is so called mixed potential. We will come back to this. Remember this terminology, mixed potential. We will come back to this. What is this mixed potential? Over potential and polarization. Okay, we first of all will identify them as the two parameters which are equal to each other with the aid of the suitable reference electrode, for example a column electrode connected to an electrode under test to form a galvanic cell. The voltage of such a cell is then measured in the presence and in the absence of the polarizing current. Two values are obtained whose difference is the over potential or the polarization. The over potential, which is generally positive when the experimental electrode works as an anode, when the current is positive, or negative when the current is negative. Will in general assume a stationary value after an initial period of adjustment. A plot of these stationary values of eta, the over potential, as a function of I, the current, is termed as the over potential current curve. The initial slope of the over potential current curve is d eta by di is also called the polarization resistance. Since the charge E is equal to it, the polarization capacitance per unit area is defined by dE by d eta, which is equal to I dt by dN. This is the Ct. Okay, the initial capacitance when time is equal to 0 is identical to the capacitance of the electrical double layer. The E eta curve must therefore pass through a finite initial slope corresponding to a finite capacitance of the double layer. The differential polarizability at any time t is defined by the reciprocal of Ct, that is 1 over Ct is called this parameter. The overpotential can be ascribed for three principal classes. Note that carefully, it is only three principal causes. There can be other causes. During the passage of the current, the activities of the reactants near the electrode surface undergo a change, resulting in a corresponding alteration in the equilibrium electrode potential. So therefore, this is a concentration over voltage. An additional over potential may be required to enable the charge carriers to cross the intersection. This is the over potential, transition state over potential, or reaction over potential. The incorporation of the atoms into the lattice of the electrode or reverse process, that is zinc is getting dissolved as it is zinc 2 plus, or zinc 2 plus is getting deposited as zinc. This is called the crystallization over potential. You would have heard many other over potentials, but these are the principal classes. The observed total over potential may thus be resolved into three additive components: the concentration over potential, the transition state over potential, and the crystallization over potential. You can put ohmic over potential, other terms also. The concentration over potential can be further subdivided into diffusion over potential eta d and reaction over potential eta r. The diffusion over potential is caused by the diffusion of the or enrichment of the reactants at the electrode surface. When silver nitrate solution is electrolyzed using silver electrodes, the silver is dissolved from the anode and gets deposited at the cathode, and the total concentration of silver ions remains unchanged throughout. An increase in the concentration of silver ions will, however, be observed at the anode because silver is getting dissolved as silver ion at the anode, while a corresponding decrease in concentration occurs at the cathode. Even when the electrolyte is vigorously stirred, concentration gradients of this type within the layer adhering to the electrodes may be overcome by diffusion. To understand the cause of the reaction over potential eta R, it should be realized that the potential determining transition reaction may be preceded or followed by chemical reactions whose rates are slower than its own. The equilibrium concentrations required to produce irreversible will not be established in time. So therefore the potential will be different. The slow step may therefore be regarded as the inhibiting the establishment of irreversible. Whenever the observed potential is not equal to irreversible, there is an overpotential. Crystallization overpotential is treated as a special type of overpotential and is observed when inhibiting steps consist of addition of metallic ions to the crystal lattice or the separation from the lattice. The resistance over potential, which we have not considered before, eta corresponds to the ohmic potential drop at the electrode and can be due to the presence of surface films. Whenever you have your electrode dipped into an electrolyte, there is a surface film. So therefore, the total over potential may be an algebraic sum of the various components. Here I have put that eta will be equal to eta t, okay, eta y, eta d, eta r, like that. All over potential have to be added. The resistance polarization eta, the transition over potential nt, are characteristic irreversible reactions and are therefore collectively termed as irreversible over potential. On the other hand, since deviations from the equilibrium potential due to changes in the concentration of reactants are largely reversible, because if I stir it or if I make the situation that the concentration is uniform, the diffusion over potential and the reaction over potential are collectively known as reversible polarization or reversible over voltage. Then there is a concept called open circuit voltage. It is the voltage that can actually be measured at the terminals of an idling cell and is commonly used value for a cell at a given time under no load conditions. This value is generally different from the often calculated on the basis of thermodynamic data theoretical open circuit voltage, which is equivalent to the electromotive force of a cell and determined under conventionally defined standard conditions. EMF is always defined under standard conditions. So activation over voltage is the voltage loss caused by the charge transport or transfer of any material or process that has a limited speed. That is, the activation over potential results from the slowness of one or more of the intermediate steps in either one or both of the electrode reactions. It can be anodic dissolution or cathodic deposition. The open circuit voltage EA is generally less than the thermodynamically reversible potential ER for the specified conditions of temperature, pressure, and activities of reactants and products because of the interference caused by adventitious reactions of impurities. In the electrolyte, there can be other species that will also undergo reactions. Therefore, there will be the equilibrium potential and the reaction potential will be different. When the net current drawn from the cell is small, cell potentials may tend to be controlled by these impurities. However, due to their low concentrations, impurity effects are small at high currents, because when you draw a high current, the main reaction is because of the electrolyte that is present. Further, it is found that at low current density, there is a very sharp decrease of potential with current. This type of behavior is characteristic of highly irreversible process and is caused by activation over potential. These limitations can generally be overcome by employing an activation catalyst or active catalyst by increasing the temperature, which is already known to us. Concentration over voltage. It is the voltage difference caused by the diffusion process due to the pressure gradients and the changes in the utilization rates of the gases or liquids, because we are not talking about only solution phase reactions. The delay caused in reaching the steady state conditions or the absence of equilibrium conditions as a result of the current flow using up or producing materials or sources of concentration difference. Other factors could be porosity of the material that influences the gas and liquid flow, or the permeability of the membrane, changing the ionic flow. Transfer voltage, over voltage, at sufficiently high rates, most heterogeneous reactions pass over into a region where they are controlled by the rate of transport of the reactants to or products away from the electrode. There are two causes for mass transport control in electrochemical energy converters, which is often used porous electrodes. The potential of one of the electrodes, rarely both together, reaches a value at which it demands a greater rate of supply of the reactant. If I were to go on changing the potential, the electrochemical reactions will become faster. Therefore, the supply of the reactant to the electrode surface will become controlled. So, then the rate at which the diffusional and conventional processes can supply. Under these conditions, the current can no longer increase with the change in potential. The other cause of mass transfer polarization is characteristic of only porous gas diffusion electrode. It is caused by the holdup of in the supply of the gas to the electrode electrolyte interface. This occurs when the rate of diffusion of the gas through the electrolyte free part of the pores becomes equal to or less than the subsequent steps with respect to diffusion of gaseous reactants into the electrolyte and the electrochemical reaction of dissolved reactant in the electrode electrolyte interface within the pore. Essentially, it is changing the concentration at the inside the pore. Resistance over voltage, it is not related to any chemical process at the electrode, and is simply the voltage drop across the resistive components of the cell. Okay, it is given by eta R is equal to IR. Okay, where Ri is the internal resistance of per square centimeter of cross section of the cell. Resistivities of aqueous, molten, solid electrolytes are of the order of 1.1 and 10 ohm centimeter respectively. When porous electrodes are used, as in the case of most electrochemical energy converters, not only the layer electrolyte between the electrode and the cathode, but also the electrolyte within the pores contributes to the electrolyte resistance. The ohmic overpotential is the simplest cause of loss of potential in an electrochemical energy converter. It may be thought that the reduction in the thickness of the electrolyte layer between the anode and cathode would eliminate ohmic overpotential. However, thin electrolyte layers may cause intermixing of anodic and cathodic reactants, thereby reducing the Faraday efficiencies. We will come to these Faraday efficiencies little later. Even with these electrodes, ohmic overpotential may arise due to sections of the porous electrodes. In the case of high temperature fuel cells, ohmic overpotential may be a necessary part of the heat balance. We will come to it. What is the heat balance? What is the high temperature fuel cells and all that. An electrical double layer exists whenever two phases are in contact, except in the case of gas-gas, non-polar liquid, or gas non-polar liquid surface. In those cases, we don't have the electrical double layer. In general, all deductions on the rates of charge transfer reactions assume that the surfaces where reactions occur are smooth and planar in macro sense, that is, electrodes are in the form of foils or wires. Here we thought about the porous electrodes. In fuel cells, however, due to the need for improved mass transport conditions and probably greater effective area per apparent geometric area of the electrode are always porous. General properties of electric double layer. At an interface, there are regions where the electrical field strength is not equal to zero. Okay, field strength. I hope you understand. The electric field arises from the presence of excess of electrically charged particles such as ions, electrons, and oriented dipoles. The region in which this excess of charge is present is called the electrical double layer. I hope you understand this. What is meant by electric double layer? When there is an charge accumulation as compared to the bulk. The presence of the electric charges in the interface affects the interfacial tension. Definitely, if you charge an electrode, therefore there is a tension. If one of the phases is a metal or a semiconductor and the other is an electrolyte solution, as we are talking about in electrolytic cells, then the changes in the interfacial tension due to the presence of charges in the interface is called electrocapillarity. Let us consider the electrode-electrolyte interface. In this case, electrical double layer is called the electrode double layer. The excess charge in the metal QM has to be balanced in the solution by a charge of identical magnitude but of opposite sign Q1. This must be the charge in the electrolyte medium. QM is the charge in the electrode. This charge is extracted from the solution by electrostatic and other forces, chemical, van der Waals and other things. Then the following relationship holds good. Qm plus Q1 must be equal to 0 or Qm must be equal to Q1. But in the sense of the uh, sign, they have to be different. The excess charge of the on the electrolyte side of the interface is dispersed perpendicular to the interface towards the bulk of the solution, while that of the metallic side has a even in molecular dimension the properties of a plate condenser. What it means is the charges in the inside the electrode is the excess charge is accumulated at the skin depth, whereas in the solution side it need not be skimmed. It can have certain depth of the solution. However, in a semiconductor electrode, the excess charge on the electrode side of the interface is also dispersed. We are going to deal with this when it is a semiconductor electrode. It is different from that. In space charge density, okay, now we have thought that there is a charge accumulation due to diffuse dispersion of the charge is related to Q1. In the solution side, the charge is diffuse. So we have to look at that and then integrate over all the space and get the excess charge. The limits of this integral are determined by considering the electrolyte as a semi-infinite medium with a space charge on the solution side of the double layer spreading to distances x of the order of few hundred angstroms in dilute solution. The space charge is usually expressed in microcoulombs. Hello? Simple case. Are you there? Okay. Shall we continue or you have some questions? In the simple case of electrostatic attraction, the ions in the electrolyte can approach the interface to within distances given by their inner solvation sheets. So that I will make sure all these things are clear to you. So that only a monolayer of solvent molecules is situated between the atoms of the electrode and the bare ions. Okay, what it means is, if I have an ion, I have an electrode. Where is the solvation sphere? So we assume, this is an assume that when the ion is very near to the electrode, the solvation sphere is very limited. That is what it means. The plane through the centers of the ions at the minimum distance from the phase boundary is called the outer Helmholtz plane, while the region between the outer Helmholtz plane and the surface of the electrode is called the Helmholtz layer. The electrostatic forces are unable to hold all these ions that form the excess charge Q1. Q1 is the excess charge in the electrolyte medium at the minimum distance from the phase boundary, since thermal motions continuously disperse them away from the electrode. So therefore, it is only an hypothetical situation. It is only an integrated over a distance that this can go on changing because of the thermal motions that are present in the electrolyte. This is how the diffuse part of the double layer is formed. Because of the thermal motions, the charges need not be accumulated as we have defined. It is defined as that region of the double layer lying between the outer Helmholtz plane and bulk of the solution. When only electrostatic forces are exerted on the ions, the whole charge Q1 in the solution side is situated at this part of the electric double layer. It is situated in the inner and outer Helmholtz plane. It is not present in the bulk. The ions can also be influenced by forces other than Coulombic forces, such as van der Waals force and chemical forces, which cause the so-called specific adsorption of ions, which we have not so far discussed. We only said the ions in the solution side is dispersed, but it can also be accumulating at the electrode surface. That is what is called the specific adsorption of the ions. It will also affect the double layer. We will come to it. So therefore, taking all these postulates into consideration, there are various models that are possible. The one is called the Helmholtz model, which is I will show you a picture I will show you immediately a picture. Helmholtz model is this: that when I negatively polarize my electrode, the charges are at the surface and the positive ions are at the very near to the electrode surface. So therefore you can see that it is a capacitor. Therefore the potential can be as a function of the distance. We can see that the potential drops very seriously up to the distance of hx, whereas this xh is Helmholtz plane. Okay, this is Helmholtz plane, is only one layer thick in the Helmholtz model. Okay, whereas Guy-Chapman model, they said no, it is not like that. This is the charges cannot accumulate like this. Therefore, they said the charges are the negatively polarized electrode like this. The positive charges are, now if you look at it, the net positive charge is more than the net negative charge here. But in the solution, it will be electron neutral. Please remember that. So therefore, they said that the, the the model that must be applicable is not a compact double layer, it should be a diffuse double layer. Then Stern came up with the idea, no, that cannot be true. It should be a combination of both of them. Okay, in the immediate vicinity of the electrode, it should be a compact layer. In the little away from the electrode, it should be a diffuse layer. Now, following this, Graham brought a concept called the triple layer. Okay, this is the, I hope you are able to see. Maybe there is a picture I can show. Okay, you can see that there is a compact layer, there is a diffuse layer, there is a, therefore what he said is it is asymptotically decreasing. Okay, so this is the Stern model I have shown. We are not drawn a picture for the Graham's model, but it is triple layer. Assume that instead of two compact layer and diffuse layer, you have compact layer, diffuse layer, and dispersed layer. Then it will be a three-layer concept. Then there is a model coming out of Bockris, Devanathan, and Mueller. That is what is called the solvation sphere. I hope you are able to see. Here, this is what I was talking. When I take an ion here, the solvation, these are all the solvations. The B sign is the solvation. The solvation of the ion very near to the electrode is different from the solvation of the ion in the bulk of the electrolyte. I hope you are able to see. It is 4 or 6 or whatever it is, the solvation number, whereas the solvation number of the ion very near to the electrode is only limited, less than the normal solvation number in the bulk of the electrolyte. So therefore the potential will, how it will drop in many ways. So here I have shown the inner Helmholtz plane, how the potential is dropping. In the outer Helmholtz plane, how the potential is increasing. Then in the bulk of the solution, how it reaches the steady state potential of the system. So therefore we will there is yet another model which we will take it up later on. Okay, there are chemical models are also available, which are all only hypothetical models at this point of time. I have not dealt with these models in detail because they are not of direct relevance, unless otherwise you are going to work on electrochemistry. We are only looking at the using this concept in the fuel cells. Okay, the first model for the structure of the double layer is analogous to parallel plate model. So we can easily calculate whatever we want to calculate. Now, if you take the next model, consider that the charges in the solution side are not located in one plane but diffuse. That is a Guy-Chapman model. This model yields a parabolic dependence of capacity on charge. Here it was, I hope you saw, here the capacity is only very steep rise. Whereas if you go here, in this model, the is the capacity changes parabolic dependence on capacity on charge. Though this model is satisfactory for very dilute solutions, for concentration solutions it is not valid. There are various other reasons, we will not go into all of them. However, in very dilute solutions it become in practice identical to Helmholtz model, that is compact double layer model. In the region of constant capacity, the dependence of capacity on the radius of the ion present in the solution is not seen, though the model shows it. It cannot also explain the increase in capacity which occurs in the anodic region. Anodic region because of the concentration changes are three-layer model, Stern's model, the metal surface, an inner Helmholtz layer, and the locus centers of the specifically adsorbed ions, and an outer Helmholtz plane, that is the locus of the centers of the first layer of the hydride ions, has several satisfactory features. However, it does not provide a satisfactory explanation for the constant capacity observed in the negative branch of the hump of the anodic side. Okay, certain observations it does not explain, that is all. In all these models, the role of water was ignored. Role of water or solvent, you see, take the solvation, even though it is the predominant species in solution, because I already told you, in all electrochemical experiments we are only using very dilute solution. The current accepted model is that of the electrode is covered with a layer of completely oriented water molecules. Since absorption, I hope you have seen the model, it has a completely oriented by water molecules in which the ions are penetrated. Okay, the current accepted model is that the electrode is covered with a layer of completely oriented water molecules. Specific adsorption of ions occurs in certain regions of potential by the replacement of the some of the water molecules by partially desolvated ions. That is why we said the solvation of the ions very near to the electrode is limited. The second layer of water molecules is not oriented because these water molecules are under the influence of both electric field and thermal fluctuation. They are like a secondary hydration sheet around an ion. Some of these water molecules can belong to the hydration sheets of the layer of the ions that are present in the outer Helmholtz plane. The dielectric constant of the first layer of the oriented water molecules can be taken to 6 to 7. Please remember, and that of the secondary partially oriented water layer can be 30 to 40. And pure water, you know very well, I don't have to tell you. Considering the double layer has two capacitors in series, one with a low value of epsilon is equal to 6, and the second value is dielectric constant is 40, the region of constant capacity with the potential can be understood. So these are all the things that are possible. It is a purely a theoretical situation. So we are going to take up next time the solid metallic electrode. Okay, why are we looking at metallic electrodes in electrochemistry first? That question has to be answered. After that, we have to look at the other semiconductor electrodes and ethics. Any questions you can ask? Anybody there?